Let us solve the problems on DFT of some of the general sequences given. So compute the endpoint DFT of the sequence x of n equals a to the power n 0 less than or equal to n less than or equal to n minus 1. So writing the formula of DFT, x of k summation n0 to n minus 1 x of n wn to the power kn. Let's substitute for x of n0 to n minus 1 a to the power n wn to the power kn. So since both are exponentials, we can combine them and write it as a single term. That is a wn to the power k whole to the power n. Now, an important formula which you can remember to solve such problems is summation n0 to n minus 1 a to the power n. What is the value of this summation? 1 minus a to the power capital N divided by 1 minus a, provided a is not equal to 1. Because if a becomes equal to 1, then the value of the summation becomes infinity. So making use of this into the given problem, the value of this summation will be a wn to the power k whole to the power capital N by 1 minus a wn to the power k. That is the DFT x of k. So you have to make sure that the denominator doesn't become infinity, 0 at any point, so that x of k becomes infinite, right? So here the value of a will be less than 1 or more than 1. So it doesn't become 1 at any point. So even if you put k equals 0, right, the denominator will be 1 minus a. So for no value of a or k, the denominator is 0 and the value x of k becomes infinity. So for all values of k, this will be a finite value, right? Then, can we simplify this further? Yes, in the numerator, we have this term wn power k into capital N. We can simplify this, right? So what is the value of wn? E power minus j 2 pi by n, k into capital N. Capital N gets cancelled. E to the power minus j 2 pi k, integer multiple of 2 pi. So cos 2 pi minus j sin 2 pi. What will be this value? It will always be equal to 1 for any value of k. It will always be equal to 1 for any value of k. So we can substitute that here in this formula. Therefore, this becomes 1 minus a to the power n divided by 1 minus a wn to the power k. That is your x of k for k from 0 to n minus 1. So given the value of capital N and a, right, you can always find the sequence x of k in the range 0 to n minus 1. But this is a generalized signal that is given to you. So even the DFT x of k which we get will be in the generalized form. The next problem, find the endpoint DFT of the sequence x of n e power j omega mn, n in the range 0 to n minus 1. So this is again a exponential signal which is given to you, right? But in a different form than what we did the previous problem. So here the value of omega, that is your angular frequency, is 2 pi by n, and m is an integer. M is an integer. M is an integer. Okay, so let's find the DFT of the sequence. So x of k is summation n0 to n minus 1 e power j omega mn wn to the power kn. Wn to the power kn. Here, this exponential signal e power j omega mn, can we write it in the Tweedle factor form, that is Wn form? Okay, let's see whether we can do that. Yeah, so consider e power j omega mn. Let us substitute for omega. So e power j 2 pi by n m into n. M into n. M is an integer. So what is Wn? The notation of Wn is e power minus j 2 pi by n. This is the notation for Wn that we are using. So if I have to write this exponential as Wn, then it will be Wn to the power minus mn. Minus mn. Right? So let us substitute that here in this summation. So summation n0 to n minus 1 Wn to the power minus mn Wn to the power kn. Now we can combine both the terms into a single term. Therefore, this becomes summation n0 to n minus 1 Wn, right? So numerator can be combined and written as k minus m. Okay, the whole raised to the power n, because n is common there. Now let's use the summation for this. Summation value will be 1 minus Wn to the power k minus m. This is the term inside the bracket which we have. The whole raised to the power, it becomes capital N now, using the value of the summation. 1 minus Wn to the power k minus m. Now, just observe the denominator. M is an integer, right? So, there is a possibility that k will be equal to m. For some value, k could be equal to m. So, when k becomes equal to m, what happens to the denominator? It becomes 0. So, x of k becomes infinity, right? So, this condition we have to avoid, right? So, the value of this summation is true for all values of k except k equal to m. So that means when k is not equal to m, the value of this summation holds good. The value of this summation holds good. For any value of m you can take, but it should not be equal to k. K should not become equal to m. In that case, the value becomes infinity. So k should not be equal to m. Only then the x of k value will be this right hand side term which we have written, right? That's one point. Then your numerator term, that is this term in the numerator, we have Wn to the power k minus m whole power n. Let's just observe this. If you want, you can split it up. So Wn power k into capital N into Wn power minus m into capital N. What is this term? Each of the term, isn't it equal to 1? Right? What we had written previously. So e power minus j 2 pi by n, if you're going to substitute for the Tweedle factors, You can substitute and see. E power plus j 2 pi by n m into capital N. So capital N is getting cancelled. Capital N is getting cancelled in both the places. So what is the value of this exponential? It is always equal to 1. So the numerator becomes what? X of k is 1 minus 1 divided by 1 minus Wn power k minus m. So one condition is this, k should not be equal to m. But what is the value of x of k in that case? It is 0. So it is 0 when k not equal to m. So for all values of k it is 0 except for k is equal to m, because I cannot substitute k is equal to m in that summation. So how do you find out at k equals m, what is the value of x of k? How do you find out? So you can go to the equation x of k directly. That is which equation? Take this equation and substitute k equals m into that summation. Okay, so the value of the summation holds good when your denominator a is not equal to 1. That which I had told you. Now, instead of writing the value of the summation, go to the summation directly and substitute k is equal to m. Then we are going to find out what is x of k at k equals m, at k is equal to m, right? So if I do that, so at k is equal to m, at k equals m, what is x of k? X of k summation n 0 to n minus 1. So now if you put k is equal to m there in that equation, it becomes wn power 0. Wn power 0 whole to the power n. Wn power 0 is what? It is nothing but 1, right? So 1 to the power n is a 1. 1 to the power n is 1. If you had minus 1 power n, then it's a different issue. You'll have to add 1 minus 1, 1 minus 1 like that. But summation of 1 power n is an integer. For any value of n, 1 power n will be a 1. So you are going to add 1 n times, right? That is the summation. Summation of 1, n from 0 to n minus 1. So you have n terms, capital N terms in this summation, or you are adding 1 n times. So what is the value of this? It is equal to n. So it's equal to n when k is equal to m. Now let me write this equation for you. That is what is the value of x of k. So what did we obtain? X of k is 1 when k equals to m, and it is 0 when k is not equal to m. So what signal is this? What sort of a signal is this? So it's an impulse function, right? At defined where? At k is equal to m. At k is equal to m. So, I'm sorry, this is n, right? It's equal to n. So n into delta of k minus m. N into delta of k minus m. Therefore, that's an impulse function defined at k equals m and having a amplitude of capital N. The next problem is find the endpoint DFT of the sequence x of n is equal to delta of n. So now let's find the DFT of the sequence. So x of k summation n0 to n minus 1 x of n wn to the power kn. So an impulse function is a signal which is defined at the origin, n is equal to 0, and is having an amplitude of 1. So this is the impulse function which we have already learnt. So let's expand this summation. It's x of 0 wn power 0 plus x of 1 wn power k, and so on up to the last term, x of n minus 1 wn power n minus 1 into n into k. So let's substitute the values. What is x of 0? X of 0, that is delta of 0, is equal to 1. That is the value which is defined at the origin. Wn power 0 is a 1 plus x of 1, x of 2, x of 3, all other values are 0, right, for an impulse function. So remaining all terms will become 0, and the DFT x of k for an impulse function happens to be 1. So this is quite expected, right? Because we have seen before, even for Fourier transforms and Fourier series, the frequency domain representation of an impulse will be a constant in the other domain. So an impulse in one domain will be a constant in the other domain. So the same thing is what we have obtained here also for an endpoint DFT. So x of k will be 1 for all values of k. So k could be anything from 0 to n minus 1, right? It will be constant and will be at a value of 1. Next problem is to prove summation n 0 to n minus 1 wn to the power kn is equal to n into delta of k, or that is as same as having a value of n when k is equal to 0 and 0 when k is not equal to 0. So this problem is not to find the DFT actually, right? Instead, it is to prove that the summation of the Tweedle factor Wn power kn will be n into delta of k. So such kind of problems we come across when we apply the properties, and you can also make use of this relationship there whenever it is required. So let us consider the left hand side, that is summation n 0 to n minus 1 wn to the power kn. So we'll apply the summation formula which we have known already. What is that? 1 minus wn to the power k, right, whole to the power capital N, divided by 1 minus wn to the power k. So let's substitute for this Tweedle factor. Let us substitute here for the Tweedle factor as e power minus j 2 pi by n, right? Then we have k and capital N here, divided by 1 minus wn to the power k, wn to the power k. So in the numerator, your capital N will get cancelled, and e to the power minus j 2 pi k, as you all know, will be equal to 1. So the numerator becomes 0. Now, how about your denominator? So denominator, for what value of k, or is there a possibility that you substitute some value of k and the denominator becomes 0? So this we have to avoid, right? So we cannot use this value of the summation for k equal to 0. Am I right? Because if you put k is equal to 0, then your denominator becomes 0. Wn power 0 is 1 and 1 minus 1 will be 0. So this value of k, that is k equals 0, we cannot use in this expression, right? So k should not be equal to 0 for this summation to exist. What will be the value of the summation? Value of the summation is equal to 0 for k not equal to 0. So we have evaluated the summation, and for k not equal to 0 we found that the value is equal to 0. Okay, so if you look at the problem which is given to you, it says for k not equal to 0 it is 0. So one condition we have got. Then what is the value of the summation when k equals 0? So let's see that now. How do you evaluate that? In the summation, on that is the left hand side, we will substitute k equals 0. And let's evaluate that. Sorry. Okay, so in the summation at k is equal to 0, let us evaluate the summation n0 to n minus 1 wn to the power 0. So that is summation n0 to n minus 1 1. So adding 1 n times, you have terms from 0 to n minus 1, so there are a total of n terms, and adding 1 n times, this is going to be n. So the summation value is n when k is equal to 0. Right? So what is the value of the summation which we have evaluated? Wn to the power kn is equal to n when k is equal to 0, and it is equal to 0 when k is not equal to 0. So what function is this? It is an impulse function, right? It's an impulse function defined at k is equal to 0. So that is n into delta of k. N into delta of k. So we have proved the given relationship.